Hey everyone. So welcome to this second part of this mini course or series, as you can call it, where we're going to code up a neural network that can play tic tac toe.
The end, we'll have something like this, which is a simple app I've set up in Streamlit, where now the neural network that we're going to be training is actually playing on the computer side, and it can actually learn how to play this game, right? As we are seeing here, it's not doing a very bad job.
Now, in the first part, we set up the problem, we set up the architecture of the neural network, a multi-layer perceptron using conventional simple training, no reinforcement learning or something like that. But an interesting classification problem, right? So we have this tic-tac-toe board, for example, and we're able to convert it into an input number state or a vector, which can be passed into the multi-layer perceptron. And the perceptron should be able to tell us, assuming it's playing as O, it's able to tell us that actually it needs to place the O here. So in the previous video, we had set up the input state for this. That board effectively became this, where you can think of each position on the board, right? In this case, each cell being a corresponding value in the number, a corresponding position in the vector. So that's cell 1, cell 2, it's all the way to cell 9, where I'm saying 1, 2, 3, 4, 5, 6, 7, 8, 9. And then if it's empty, it's -1. If it's X, it's 1. And if it's Y, it's 0. And then the last vector, so you have 9 states corresponding to each cell in the board. And then you have the 10th state, which is who's playing next, X or O. And we're making that an input because we know I've played and then the computer is playing. So, and vice versa. So we're making that an input to the neural network. So the input to the neural network is basically a vector of size 10. And then the output is what the computer is going to do. Now it knows whether it's X or O. Let's say it's playing as O. What it needs to do is pick which cell to play. Now, in the previous video, in the first part, we set up the output as 9 cells, right? Any of the 9 cells, and whichever cell it's going to play in, the output is basically the one-hot encoding of that, should be the one-hot encoding of that. So our data set is going to feature the one-hot encoding, meaning every cell where the move should not be played is set to 0. And the cell where the move is going to be played, in this case, it's the last cell, so the 9th cell is set to 1. And that's what the neural network should try to output. Now, in reality, we'll see even when it's trained, it will not be 0 and 1. It will be some set of values, but the maximum value corresponds to the cell that the move is placed in. This is our training data set where we're saying we know for sure the next move should be here. And we've seen that we've got this data by simulating a number of tic-tac-toe games using the Minimax algorithm, which is another machine learning algorithm that can be used for gameplay. Now, I've added a plus here because we're going to add in this video one more state to this, and we're going to add it as the first state, right? So this state we've added, which is what if the board is complete and there is no more move? Now, ideally, the computer actually you'd have, when we implement this, we'll see when we implement this in Streamlit, it would actually call a function to check if the game is over. However, when we trained the network, we had, or rather when we got the data for the network, we had examples of data points where no move is possible. So just to see if the network's able to learn that, we added this one state here. So the first state corresponds to the network saying no more move is possible. And then all the other states now, so this 1, 2, 3, and so on, all the way till 9, are the potential output cells. So if it gives you a 1 here, it means you can't play anymore. The game's over. If not, depending on which of these cells is, it will play the move in that. And the input will tell it whether it's an X or an O. The output is just which cell to place the X or the O in. We set this up in quite a bit of detail in the previous video, so you can go and refresh your memory with that. So we can now get coding with this. As I mentioned, we're going to be using PyTorch. The whole idea is to kind of give you an understanding of how to quickly set up a classification problem in PyTorch, right? In the previous series, we looked at, which was the neural networks for classification with the email classifier. We'd set up each of these pieces of the classification problem in step-by-step detail. We'd implemented it. So I'm assuming that if you have any doubt, you can go check that out. But in the previous video, we've seen the basic steps. And now as we implement it, you'll start seeing the pieces of the neural network coming into play. Okay, so let's first quickly just kind of go to the PyTorch website to take a look at that, and then we'll start coding.
So to get started with PyTorch, you can go to pytorch.org, right? And you can go check this out. They've got really good documentation. Now, if you go to learn, right, and you click on get started, you also have, basics and so on. So if I go to get started, you can pick kind of which version you want. You can pick whether it's Linux or Mac or Windows or whatever, and then accordingly you can use the command. So in this case, if it's a Mac, it says you can use pip and you can install that. If it's a Linux machine, it does that, and that's all you have to do. You can also use Anaconda or Conda to set this up as well, but I kind of just did this and got myself set up. So it's pretty easy to install. It's a very widely used library, so I will not run through this a lot more, but you can go check this out, and I can add a link to a YouTube video, not mine, where it kind of shows you how to get set up with PyTorch, right? So we can do that as well, but this should be pretty straightforward. And so once you've got Torch set up, let's go and start coding. So the code for this app that we're going to be writing, or rather for both the Jupyter Notebook that we're going to be coding up now, and then the PyTorch app, rather the Streamlit app that we're going to be setting up, is here. So you can go to github/pexagon and then to the Tic Tac Toe NN folder, and you can see all the code that we've written. So the Jupyter Notebook that you can try, the input data, and the Streamlit app with the weights that we've trained it with, right? So do check that out, and that will help get you started so you can experiment with this. That being said, let's now go start coding it up. Okay, so let's get started, and we'll start by quickly just exploring, what a torch tensor is, because that's what, our neural networks will be built on. So assuming you've got, so I've created this file called tic-tac-toe NN, as and let's start by first importing torch, right? So I'm importing it, and now let's create a tensor, right? So tensors are the torch equivalent of NumPy arrays, right? So kind of like what you can do with NumPy. If you say torch.rand53, it creates a 5x3 vector, or in this case, it's a PyTorch tensor, right? So it's got 5 rows and 3 columns. This is pretty similar to what you'd see in NumPy, right? So if I say now, let's say y is torch.ones, which again is something you'd see in NumPy. What is y going to be? Can you think for a second and see what you'd get? You'd basically get something with the same dimensions, which you need if you want to do matrix operations or tensor operations in this case, and you get the a 2-dimensional matrix here, 5 rows, 3 columns, everything is 1. So now if I say z is equal to x plus y, and I say print z, what do you get? You get the sum, right? And it's very easy. It's 1 plus this, so it's 1.97, 1.0798, and so on, which is again, it's a matrix operation or a tensor operation, which is again very similar to what you'd see in NumPy. So then why the whole effort of using Torch? Well, or PyTorch in our case. Answer is very simple. It allows us to build neural networks in this. Now, the two aspects of this that become key for neural networks. One is automatic differentiation, right? So, and we've got a quick series on this. So I'll add a link to that. You can go check it out. But the basic idea is, with a neural network, you'd write the forward pass, which is the different layers that the system needs to traverse, or rather the data needs to traverse to get the output. But now to train it, you have the training data, and you have the actual output, and you need to do the backward pass. So the backward differentiation part, when automated, is called automatic differentiation. The advantage here is you do not have to manually write the backward pass, because under the hood it uses torch tensors. What PyTorch will do is, once you've written the forward pass, it will start and automatically differentiate for you, simplifying the whole process. The other aspect is running on GPUs, right? And so this is exceptionally important again, because as you've probably observed, with the fact that NVIDIA is valued so highly as a company, GPUs are perfect for building and training neural networks, right? It significantly improves computational time by orders of magnitude, right? And so again, if you have to rework Torch or NumPy, to get it to run on GPUs, things get complicated. In this case, with Torch, it's exceptionally easy. You can set it very quickly with a line of code, and you can then run the exact same code on a GPU, which means training is very easy. It's also set up to parallelize across GPUs, right? So basically, if you can build your model in Torch, you can then very quickly kind of apply it for production, right? So that's kind of the reason why neural networks are built in Torch. And when you're building language models or image models, you'd use a tool like PyTorch or TensorFlow, and so on. The idea being basically these reasons, right? In production level frameworks, automatic differentiation is built in and ability to run on GPUs. Okay, so let's now start by first importing our data, right? We've kind of got a basic idea of what a tensor is. It's very similar to a NumPy array. So what we can do now is start building a network. First thing is importing the data. Now I'm going to use pandas to do that like normal. So there's a file called Tic Tac Toe moves.csv, and I'll show you that in a second. What I'm going to do is read that CSV file. Okay, right? So this is kind of what the file is. It's pretty much what we saw, in terms of input examples. It's just these board states. So that's the 9 states. Who's the next player? -1 means there is no next player because the game is over basically. If it's 1, as you can see further below, it's player X who's going to play the next move. If it's 0, it's player Y. And then you have what the move is. So if there's no move, then the move is -1, right? If there is a move, then it's the position of that move from, whatever, right? So that's kind of what the data is. And so let's first import this data with this. I haven't written pandas, so let's just import pandas. And then let's go and import your data, right? And if we can just quickly display it, we can just see what it looks like, right? So it's pretty much what we saw in that file. Now what do we need to do? We need to take out the actual predicted value, the actual value, separate that from the input features, right? Because this will be the input to the network. This is what you need to test. So what we'll do for that is we'll say, well, let's just break this down. We have the headers, and with pandas you can quickly get the pieces out. So I'm going to say X, which is the input features, are these columns, and the player. Y is move. So we've done that. And so if you print X now, you see it's got everything from here to here. And then if you print Y, it's got the move, which is from -1, but it's basically whichever value the neural network, whichever output position the neural network is going to pick. Next thing we need to do is convert this into a one-hot encoding. That is Y, right? X is fine, but Y now, for classification, we're going to be using cross entropy with softmax. And so what we need is a one-hot encoding. So you can, I've just quickly written this. It's a simple script. So what I'm doing is you've got Y encoded is number of points in Y, number of Ys, basically number of input points, and then there's 10 values. What it's doing is just looping over that and saying if Y is -1, meaning there is no move, then the one-hot encoding is 1 0 0 0 0 0. Else, in this case, the corresponding position from 1 to 9 would be set as 1. So let's just look at an example. Again, I have to import NumPy. So import NumPy as NP, and then let's rerun this. Okay, so let's just look at an example. If I say print, Y go and encoded 0, you say it's 1 0 0 0 because it's -1. If I say the same thing, so in this case there is no move, so this is set to 1, everything else is set to 0. In this case, the last kind of data point, right, the predicted move is at cell 1, right, which is the leftmost cell in the neural network, right, in the Tic Tac Toe board. So the top left cell, so if I run that, it's 0, 1, right? If you look at 5 there, let's do -2, and it's so 0, 1, 2, 3, 4, 5, and then 6, 7, 8, 9. So if this is 1, it means it needs to put either the X or the O, depending on who's the player, in the bottom right corner, right? So 5 is the middle cell in this case, and so that's the one-hot encoding for that. Okay, so hopefully that is clear. What we'll do next now is we are going to use, load this data into PyTorch. So what do we do? Or rather into a torch tensor. So what do? We say, well, X tensor, and it's very easy to do that. X tensor is torch.tensor, and X, we've just got that, here, right? And when you say df, this dot values, it's effectively a two-dimensional array. So I'm just passing that in, and I'm just saying the data type is float 32, right? So it's a floating point input. So I run that, and if we can print X tensor, you see that, right? It doesn't look very different from a typical NumPy array. It's just that it's a tensor now. So when we use this, it can backpropagate or do tensor operations or run on the GPU. Same thing for Y. So we can say Y tensor, and it's pretty much the same operation, but now it's Y encoded, right? And if we visualize Y tensor after that, so let's run this and run this, and you get effectively the one-hot encoding, but now for the different values. So this, we remember -2 and -1 and so on, and we've got the value. So -1 in this case was, if you remember, it was 1, right, which is the last value basically. The X or O was going to be placed in the first position. So we've got the one-hot encoding for both X and Y. What's the next step? So when you're building a neural network and you're trying to train it, what we do with the data is we break it down into typically a training, eval, and test sets. And what you do is you train on the training and keep evaluating on the eval. And so you could do, say, a 70, 15, 15 or something like that in terms of ratios of breaking the data. And then once you've done training and evaluating on the eval, you can then do one final test on the test set. The idea being that the test set should effectively represent the actual problem or the actual data you'd actually be testing on or evaluating in production on. If you keep training and then evaluating on the test set and retrain, then again you would effectively end up overfitting on the test set. That's why nowadays an eval set is also used, right? And so you can keep evaluating on the eval set, keep retraining, and then when you test on the test set, that effectively should be your final kind of estimate of the network accuracy. Now in our case, we have limited data points, and you'll see when we train that it is an interesting but not a very great problem to train if you leave out data. So in our case, we're just going to start with the training and test sets. Okay, so that's markdown. And so what we'll do is we can split the data, right, into a training and test set using a very interesting simple function from scikit-learn, right? So we could either write the script for this manually, code, but what I'll do is I'll import scikit-learn, and from scikit-learn import model selection or dot model selection, import training test split. So if I do that, now all I have to do is give it this, right? So if I say x train, x test, y train, y test, I pass this function the x and the y. I basically say the test size is 0.1, right? Which means 10% of the data is used for test and the remaining is training. And the random state is just a number you use for reproducibility. So you don't give this, it will randomly kind of split your data. If you give this, you can reproduce the value. So I've done that. So now actually if I just go and print the len of X tensor, right, it's 5478, that many data points. If I go and say X train, it's 4930, right? And if I say Y train, or rather, X test actually, sorry, then it's 548. So you're going to be training on 4,900 data points and then testing on 548. Now, we've in the previous video talked about having 6,000 data points. So we did have the original data set of 6,000. I've removed a few that were effectively duplicates, right? So, or rather invalid states. So I've reduced that number, and so we end up with the 5,900 number you see. Okay, so we've got a data, we've broken it down into a training and test set. What's next? It's the interesting part. It's building the neural network model. So let's go and implement the model. So when you're implementing a model with PyTorch, what you'd do is you'd start, first of all, you'd import, right? So I've imported torch here. Let's import torch nn, right? And so torch.nn is the way to import the model. Actually, what I'll do is I'll import it right where I'm writing this module so you can see where it is. So import torch.nn as nn. And now what we're going to do is we're going to create a class, right? And that class is basically right, this is going to house our neural network. And what this is going to do is inherit from nn.module. So what it does is take in the properties from nn.module, which is what we need to do so that, you know, the backpropagation is enabled and the neural network can then be understood by the optimizer and so on, right? So we'll first write the init function for this, which will set things up, and we're going to call the parent class, and then we're going to say, you know, or rather the parent class is constructor, pass in all, you know, this class and so on, right? So that will kind of allow things to work. And then what you do is typically you can here now set your layers. So as we've seen, our network is going to have a few fully connected layers, which are linear layers. And let's not worry about the activation function for a second. So we're going to call it, right, FC1, fully connected 1, fully connected 2, fully connected 3, and fully connected 4. And if you remember, when we set this up, we had a basic estimate of the size of these layers. We had started with this, right? Now you can experiment with different configurations. You can try reducing the number of layers. I found that this ratio, you know, seems to work quite well in this particular case, but you know, you can go do 10, 16, 16, 32 and then come back down and see if that works. So we obviously increase the number of neurons in the layer from 10 to 32 to 64, or 10 to 32 to 64. 10 inputs. So first layer has 32 neurons, second has 64. We're now back down to 32, and then you're now back down to 10, and this will return the logits as output, right? And then we won't use the softmax function here because the cross entropy in PyTorch has softmax built in. But what we need now is the activation function. So I'm just going to set up the ReLU as well, and we're going to say self.ReLU is nn.ReLU, right? And that's it. So we've here in this class set up the linear layers and the ReLU function. We've just initialized that, right? Okay. So now what we can do is write the forward pass. So we'll say def forward, and it takes an x, which is just the input vector, and in this case vectorization is also built in, right? So you don't have to worry about vectorizing your layers. It's just built in, which means you can train much quicker because the inputs are going to go in batch mode. So now how does this network work? Well, it'll take in its input, but what it's going to do is say self.fc1, so fully connected one layer, which is this one. It's going to take in the inputs. It's going to give you an output, and what we're going to do is now pass that output through ReLU. So this is equivalent to saying x1 is self.fc1x, and then x2 is self.ReLU x1, right? So the input to the network will go in through the fully connected layer. You'll get the output 32, and then or rather 32 outputs that will then go into the ReLU, and you get x2. Instead of that, you can just write it a lot quicker this way. And this x now, we're just reusing the variable, will be, you know, the value will be stored in it. But what PyTorch is doing behind the scenes is it's actually recording all these operations and noting what exactly is being done. And again, if you go back to the AutoGrad series we've done, I kind of show you how it does that, how it records this. So now that we've got the output of the first layer with the activation, what are we going to do? We're just going to pass it through the second layer, right? And it's x again, so it's quite simple. Let's write that for the third part as well. So self.q, and it's self.fc3, and then the last layer we're not going to add ReLU, we're going to say self.fc4. right? Now what ReLU does for us, the reason we add these ReLUs is when you keep adding linear layers, values can sometimes become negative, and it can cause problems. The ReLU will just cut that off, right? As we remember the ReLU function, as you can see here on the right, it's kind of, it's just, it's going to cut off all the negative values. So that kind of improves convergence quite a bit. And what are we returning? We are returning x. And actually that's it. That's our neural network. And so if I now say model is Tic Tac Toe, we have set up a neural network, right? Simple. And if you want to evaluate this, what you can do is you can say, well, just call the model with a data point, right? So how would you do that? Well, it's quite simple. Let's just say we have the model. Let's just say x eval is, torch.tensor. This is the input, an example input we are giving. The neural network has not been trained, by the way, and you can just say output is model, right, x eval. Now when we've initialized this, it's just being initialized depending on the initialization methodology. We haven't specified one, so it's just going to be setting up randomly. And then we've initialized the model. I've defined an input tensor, which is just this state, and I'm going to run this. And if I print the output, it gives you an output, right? And it's also telling you what the gradient function is for the backward pass. Okay, now we don't have the value there. I'm just showing you the function, right? Okay, but you see that we've effectively run this input through the neural network, and it's giving you an output. We don't know if the output is good or bad. Let's not worry about that for the moment. But we've got a neural network that's basically working. So let's now train this. Now, actually, I do know the answer to this question. The actual output in this case is 2, right? In this case, the answer is definitely not 2, right? We see the largest value, the largest output is this value, which is what? 0, 1, 2, 3, 4, 5, 6. So the neural network is definitely not giving you the right answer, right? So what do we do next? We have to set it up to train. So let's go do that. So to train the model, what we're going to do is, first thing we need to do is define our error function or loss function. So our loss function is going to be the cross entropy loss function with softmax built in, right? So it's going to be softmax plus cross entropy. You have to use the softmax with the cross entropy loss. Right. And as a result, as I just mentioned, the output here is just the logits, right, from the neural network. We haven't run a softmax there. So what I'm going to do now is, how do you set that up in PyTorch? It's very simple. Just go criterion or loss function or whatever, that's the variable name I'm giving it, is nn dot and that's it. What do we also need? We need the optimizer. So the optimizer, how do we set that up? We say optimizer is equal to, and we're going to use the Adam optimizer, which is a fairly advanced algorithm, kind of a derivative you can think of gradient descent. So what it's going to do is, say, if you say model.parameters, it's going to take the parameters that we've built here, that it's initialized, and initialize this model with that. We're going to say the learning rate is 1e minus 3, right? And we're going to say the weight decay is 1e minus 5, which means after a certain number of iterations, it's going to try and reduce the step size even further to try and converge, because as you kind of get closer to the optimum, if you take large step sizes, you just sometimes overstep the optimum. So over time, you want to reduce the weight. So I have an imported optim. Let's just do that. So you can import from PyTorch. You can just say import torch.optim is optim, and we've set up the optimizer. Now that we've set up the optimizer, let's set up the optimization problem. So that's quite simple. And I mean, just a kind of quick reminder, if you've seen the neural networks for classification, where we did the email classifier, that series, then we'd kind of set this up each step manually, right, for optimizing and creating a softmax and cross entropy, and then we made it a library called deep roots, right? And with that, we'd kind of seen a similar simple kind of breakdown of operations, just to give you the hang of it, right? Only there we had to write the backward pass. In this case, we don't have to. So first thing you want to do with training is define the number of epochs. I'm saying the number of epochs is, let's start with 1,000. Actually, let's start with something smaller. Let's start with 100, and then we can run it a little more. And then what do you want to do for each epoch? For the epoch in range num epochs. So for each epoch, one epoch, right? One epoch is one traversal through the entire training set. Meaning for one epoch, it's going through the entire training set once, right? So 100 epochs means it's training on the data, the entire training set 100 times. Okay, so now what am I going to say? Model.train, and actually let's write that above. So what that does is it tells NumPy the model is now in training mode, which means it enables the gradient calculations, right? If you don't enable the gradient calculations, you can disable it by saying model.eval, in which case it doesn't set up for gradients. In this case, we want to train, we want the gradient calculations and tracking to be active. So we'll do that. So I'm going to say optimizer.0grad. Why am I doing that? Because in a neural network, in this case, when we do backpropagation, the gradients are accumulated, right? Which means, with each gradient calculation, it's basically a plus sign that comes in. And so if you don't zero the gradients, then across each iteration, it's just going to keep adding those gradients, and they're going to become extremely large and incorrect. So you have to zero grad, after each pass or iteration. And then output is, so once you do the grad, let's run the model. So we're going to pass in the xtrain, and we can pass the entire thing in one shot. It's able to run in batch mode. So you get the output for the entire training set in one shot. And it's a fairly small data set. Then loss, what do you do? We've defined the loss here as the NN cross entropy. What do you have to give it? Well, you have to give it the output, and you have to give it the, and let's call this outputs, right? I've used output above, I think. So outputs, and you give it the training data, and the outputs, in this case, the neural network's giving effectively a one-hot encoding, right? It's because it's not one hot in terms of, it's got, as we can see here, multiple values, but it is of size 10. And here we have the Y train, which is a one hot encoding. So it's got, the size of it is also 10. Once you've got the loss, what do? You say loss.backward, and that initiates the backward pass. So it will start with the loss and pass back to the network, and then keep passing back from there. Once you've got that, so that is where the gradient calculation happens, right? Right, let's just write zero out gradients, run the forward pass, compute the loss, and then the optimizer, which we've created here, has access to this model and the loss. What it will do is, once the backward pass is run, it gets access to the gradients, and so when you say optimizer.step, it takes the step based on the gradients and the learning rate. Now what are we going to do? We want to print the output. So I don't want to print the output every iteration, so I'm just going to say if, and I can actually just copy paste this to make it simpler, which is every 10th epoch, print out the epoch number, right, and the loss. So let's run this, and it says it doesn't detect optimizer. What have I done there? Optimizer.0grad, optimizer, spelling mistake, and let's run it. So we've got 100 epochs, and you see the loss going down from 2.2747 to 1.25. So it's doing quite a good job, right? Good. So can we converge this a little more? Let's now run this for a little more and see what happens. So it runs very, very quickly, as you can see, because it's a fairly small network, and you're already seeing that it's starting to converge really well, right? The loss function is going down. Now, obviously, if you're just experimenting, you might not get such a good quick convergence. I've experimented a little with the network parameters to make sure that this works. So we've got convergence. We've seen that, this is going from 2 to almost 0, which means the network is converging, right? So how accurate is this? Let's just take a look quickly, right? So first thing we'll do is we will set the model to evaluation mode, right? Till now, if you remember above, we've set this to model.train, so it ensures that gradients are set and so on. It can train. Now when we say eval, it means we're just evaluating, and I'm going to ensure that again by saying no grad, right? Which means it's not going to compute the gradients. It knows it's just forward mode. And then what we'll do is say outputs is equal to model, and we have our test data set, so we're going to say x test. So we get the outputs. What we also need to do is try and get so we need to first, the outputs as we know are the logits, right? The softmax has not been applied to the neural network. So what's the prediction? Well, the prediction is the maximum value, right? So we can just use torch like we do with NumPy. We can just say torch.max, and we say outputs.data, right? Along, along the y-axis, right? We want to make sure that it's doing that. And then what's the actual prediction? Well, it's the value set in the one-hot encoding. So we can either take that, but given we have the one-hot encoding here, we can just take the max of that as well. Everything else will be 0, the max will be 1, so that will give us the answer. And then we want the accuracy. So the accuracy is what? Is, well, if the predicted value and the actual value are equal, right? That's kind of where it is. So this is not model, this is predicted. When they are equal, or whatever data points they're equal to, so this will set true for that, and for everything else it will be false. You sum that, or rather it will set it to 1 and the other will be 0, and then, right, and then we want this as percentage, so we're just going to, right, set this up, and we can then multiply that. And at the end of this we can say print, right, and then we can say test accuracy, and then accuracy, right, and yeah, that's it. So let's give that a go. So running this, and we get 69.70. So that means we're getting a 69% accuracy on our prediction. How good is this? Well, it's not great, right? We were hoping for more. If we change x test to x train, so let's just do that. Let's see how well it does on a training set. Now it should basically be pretty close to 100, right? And so this is y train. Am I missing anything here? And let's go and see what this does. It's 100, right? So the training accuracy, in this case, this is training, it's not test. So on the training set, it's giving you 100% accuracy. On the test set, it's only giving you 70, right? So that's a classical case of overfitting, right? Where it's able to really fit the training data brilliantly, but then when you evaluate the test set, it's not doing all that well. Now, typically a solution for this is to reduce the size of the network and redo this, right? And see what happens. So let's quickly try that. Let's make this 10 and 16, 16 and 32, and then 32 and 16, and then 16 and 10, right? So you rerun this, should be pretty quick, and let's see what happens, right? So it's converging, but not as well as it was converging before, right? Because, well, in that case, we had a lot of neurons, it was doing a great job, but as you can see here, it's starting to stagnate. So we could keep running this. If I rerun this analysis though, so the test accuracy is higher, the training accuracy is lower. So what if we run this for another 10,000 iterations? See what happens. And so it's going to start from there. Right? So you see that it's starting to converge. The error is not changing, which means the test accuracy is great at 73 and the training accuracy is 86. It's not doing any better than that. So what do we want to know next? We want to know how well this is doing, right? So I'm going to paste this piece of code here. What it's going to do is it's going to now go through our test set, right, and see what it's getting wrong, right? Which are the states it's actually getting wrong. So let's quickly run that and see what happens, right? Let's run that, and it says, that's because, well, actually it does the answer. The problem with predicted is I've used predicted here as well, right? So let's rerun this one and then go back here and rerun this. Now that should work. So we see the states for which it's actually getting the prediction wrong, right? So what it's basically doing is checking if the actual is equal to the predicted, and if actual is equal to predicted, then it's fine. If the actual is not equal to predicted, what it's also doing is checking if it's placing an X or a no in an empty cell or not, right? And if it's placing in an empty cell, it's saying true. If not, it's going to say false, right? So we're finding that in this case, it always places the X or the O in an empty cell, right? But not always the right one, right? Which is interesting, right? So let's do something. Let's quickly visualize these errors, right? So let's, I've put together a small Streamlit app where we can post in this input vector and we can kind of visualize the Tic Tac Toe board. So let's quickly go do that. So we can see where the errors are showing up, and then we can think about if we can fix this or not, right? Okay. Okay, so let's quickly visualize this, right? So I've posted the first tensor here. So it's still here. This is the board state. This is whose move it is, right? So this is the board state, you see, and it's X's move, right? X is played, O is played twice. Now, it's interesting because if you look at this, it says that the actual output is 2. The predicted is 3. So it's saying that according to the data which was generated using the minimax algorithm, X should have been placed here. It's actually placing it here. Now, if you think about it, and it has not seen, the neural network has not seen the test set, right? So it hasn't seen this exact state yet. It understands that you need to place the X here and you win the game. However, we're seeing an error because the minimax algorithm has felt that placing the X here is better. Why is that? Well, if you place the X here, now it guarantees a win for X, right? Technically, it's already won the game if it does that. So that's what it should do. But what the minimax in this particular case did is, given this state, it said place the X here. Now whether O is played here or here, X wins anyway. So we see that the neural network is not doing a bad job. It's just that the data it was given, right, that I generated, requires it to play the x here. Let's try another example. So let's try this one, right? Let's see what happens. This is O's move. This was the state of the board, right? So what's the state of the board telling you? Let's set this. This is the state of the board. So as you can imagine, x needs to be played here, right? That's what it needs to do. What is it doing? So it's saying the actual is 7, meaning that's what our neural network is telling us to do, right? Let's look at this again. Actual and predicted. So actual is what the data is. It's saying play a 7. What it's predicting is 1. So the data is saying play x here, win the game. What it's doing is saying play the x here, right? Which makes no sense because you play it here. If O plays here now, right, it stops you from winning that game. Now technically you can say again it's the same example where if you play x here, O stops you from winning here, but now you can play the x here. So it's two inverse examples, right, where in the first example it's kind of asking you to play that extra move and guaranteeing the win. In this case it's saying take the win, right? So we are seeing that the neural network, by reducing the size of the network, is now doing a decent job, and wherever it's going wrong, like we've looked at a couple of examples, we're seeing where it's going wrong, it's not asking you to place an x or an o in an incorrect position, right? Meaning something where there is an x or an o. It's basically, in these cases at least, it's kind of, trying to get you the win. In this case, it believes get the win straight away. Instead, the data is telling it, no, play an x here, and one more move later, you will get the win. So it's doing a decent job. The errors are because of how the minimax data has been generated, which means with a better data set, better defined states, it might do a better job. Okay, so we've seen how the training has worked. So that's pretty good, right? So let's now take this trained network and insert it into a game like this. So in this case, it's just visualizing the board here, but we can now take this board and in Streamlit plug in the neural network, right? And I'll show you quickly how I've done that, and play the Tic Tac Toe game that we've trained the neural network to do, right? Now there's one more kind of thing here, right? Which is the one thing we could do is, and typically for neural networks you wouldn't do that in reality because it makes no sense, right? But what you could do, because in Tic Tac Toe you know all the states of the game, in our case we know all the data sets or all the possible states that neural network is going to see, right? So what you could do is train on the entire data set. So instead of doing this x train x test, we could say, well, actually I'm just going to train on x tensor and y tensor, train on the entire data set, and we know that with a larger network, right? So if I make this 10, 32, 32, 64 again, it will fit our data completely. And if it does that, then the neural network we have, right, is guaranteed to give you the right answers, right? Because it's fitting our data perfectly. However, the reason I don't do that here is because in practice, when you train other neural networks, forget Tic Tac Toe, right? But in practice, when you're training a neural network, you are deploying it in production and you don't know that you're going to see the same data, right? In fact, you probably will not see the same data. So you need to use this approach to make sure that, it works on your training data. It might not give you 100% accuracy, but then on your test data, it does well enough that you can deploy it, right? Overfitting is generally not recommended unless you know for a fact that those are the only data points your network is going to see in production, right? Which is obviously always not going to be the case. So how do we export this model? Well, that's quite simple. You can export a neural network out of PyTorch pretty quickly, right? And how we're going to do that is we're going to say model dot export, right? And that's about it. So just 1 second, and what we can do is say torch dot save, right? Model dot state dict, right? And we're going to say it's Tic Tac Toe weights dot pth. And so what we're saving here is the state of the model, and if I run that, it's gone and exported this. So we're going to take this file now and quickly run it in the Streamlit app and see how the gameplay is, right? Okay, so let's do that quickly. Okay, so I've opened this in my IDE and I've also got the Tic Tac Toe game, right? And this is not just a state visualizer, it's actually a game. So how does this work? Okay, so I've created a file called Tic Tac Toe net, and this is exactly the net that we had previously, that we have seen in our notebook, right? And it's using only the ReLU. These are just there for backup, but it's effectively exactly the same neural network, right? So I've got that neural network here, and what it's set up to do is, once I have that, if I go to tictactoe.py, I import that neural network. I've also got a Minimax version just for testing sake, so this file will be in the GitHub repo as well. You can experiment and see how the tic-tac-toe neural network and Minimax are different. Once I initialize this neural net, what you can do is say load state dict. That's what we had exported from there. So you can import that and the neural network is loaded, right? You have the board here, you see, which is in this case stored in session state, which is what you have to do with Streamlit. So it's a 3x3 board, and then it's telling you it's starting with X, it's telling you there's no winner and so on. The three ways the computer can play the game. It can just pick a random position that's empty. You can plug in Minimax, or you can plug in your neural network. So you can experiment with this, but I'm going to focus here. What it does is takes in the board, which we've just seen above is a 3x3 array. It's going to flatten that, so it becomes the same state. It's going to, in this case, I'm assuming that the computer always plays as O. I'm always the first player, so it's going to say add this to the state. We know the input state is the the state of the board, and then who's playing next. So O is going to play next. I convert that into a torch tensor, right? And then after that, I arrange it the way I want in terms of the torch tensor, and then I feed it to the neural network. So this is the call to the neural network, and I feed that board in, which gives you the output. As we know, it's going to give you the logits. So what we need is to take the max value of that, as we did when we had the Jupyter notebook open. So we get the best move, and then this is, as we've seen there, this is going to be this is going to be the index. So what we're going to do then is convert it into the corresponding row and column values and feed that back into the row. So that particular index, if this says 5, it's going to find out in the 3x3 grid where 5 is, and then for that corresponding row and column set 0, which indicates that this is going to show O. How does that work? Well, there are a few more functions here. You can check if the game is over, you can check if it's the winner, you can check the status of the game, and we need that because what the Streamlit app is going to do is call the play game function with each move. It's going to take in the user input, and the user input, it's going to first check if the board is empty. If the board is not empty at that point, it's going to say it's invalid. Then it's going to go in here and set that state to X, right? Because the user playing is always playing as X. It's going to check the status of the board at that point. Has somebody won? If I've already won at that point, the game's over. If not, then it's going to go and compute the computer's move. Now, with the computer's move, we're not checking if the game is invalid or not, because the neural network should have figured that out. So if the neural network plays invalidly, then the game's just going to, we're just going to see that the game is going to do silly things, right? We're not checking for that. We're going to make sure that we have to make sure that you've trained it in such a way that the neural network actually doesn't produce an invalid move. And then it's going to check if, again, the computer is won or not, right? That's about it. This is the basic board. So with Streamlit, you can set up the title. This is some of the formatting. And then it's basically displaying a 3x3 grid where each element here is a button. And then depending on the session state, it sets it to X or O, right? And if you win the game, it says winner. You have a restart game button. So I've run this. Let's just start playing. Let's say X. So it says O here. Okay. So let me say X here. It says O there. Okay, let me play X here. It says O there. Okay, it's not doing very badly, right? I say X here. So it blocks my move. I say X here. It's a draw. Not bad, right? So this is a neural network, by the way. Let me just go back and keep that function open. So it's calling check compute move NN, right? Just to make sure, and compute move NN is calling a neural network here, right? So I can even write that here, calling the neural network, right? Perfect. So let's restart the game. Let me play an X here. So that's O. Okay, let me try this. So it's blocking my move, not bad. Let's try this. Good. Now what happens if I know in this case I'm supposed to play the X here to block the computer's move. But the problem is, then what about this? The computer's already won, right? So I play this and it wins. So not bad. The neural network's pretty smart. Let's try another one. Okay, I do that. Now see, it's goofed up here, right? Because now I win the game. So I do that and I win. So we're seeing that there are those states, which is what we saw there. It's not playing an invalid move because we're not checking for the invalid move here like I showed you, right? If it plays an invalid move, then it would play the O in a place where the X is already there. It's not doing that, but in this case, it should have put an O here. It's not getting that fully right? Okay, let's try another example. So that's where the training error comes in. If I say X here, it's blocked my move. Okay, I do this. It's blocked that. I do this. Not bad. Not bad. Let's try another one. And so I do that. And then play that. And it wins. Okay, so it's actually doing quite well. There's the odd game that it does lose. Now, what can you do in that scenario? That's where you can go and overfit your neural network. And if you overfit your neural network, then it'll pretty much win every game, right? It will, So go and try that out. See what happens when you overfit the neural network. And actually, I'll add the weights there. I have the Tic Tac Toe weights overfit here as well, which I'll commit to the repository. So I've actually tried that out. And in that case, when you go to TTT.net, use these weights, right? Use the 10, 32, 64 weights because that's the weights I've used. And you will find that with that case, tic-tac-toe is going to be perfect, right? In the sense that the computer is not going to let you get away with it. Okay, so hopefully the idea of this experiment here was to give you an understanding of how you can set up a neural network with PyTorch, and also quickly review how you can set up a classification problem even for something like a game like tic-tac-toe, right? Now in the neural nets for classification, where we did the email classifier, we actually went through every piece of the puzzle. We implemented it as well. So you can kind of refresh on that, go back there and refresh the individual concepts. But in practice, whether you are training a language model or an image model or a game or on other kinds of data, effectively for classification, this is kind of what you'd have to do. This is kind of how you set it up in PyTorch. Okay, so let's play one last game and hopefully I can win. And I did, right? Because the neural network should have played the O here and it didn't. Go and try this out with TTT weights overfit and you'll find that it catches that move very quickly. Okay. So on that winning note, I'm signing off for now. Hopefully you've enjoyed this series of a couple of videos where we've implemented how a neural network can play this game in PyTorch. See you in the next one.